welcome to another episode of Pure Electronics, getting your hands dirty without programming or using any microcontroller. Let's assume you walk into a dark room. The first thing you do would be to switch on the lights. I guess that's too spontaneous, you might have missed that. Let's switch off the lights and begin again. Focus on the switch on the bottom screen. You flip the switch and then the lamp comes on and just lights up the entire room. I expect everyone to be familiar with this because we flip switches on a daily. However, today we will be looking at a different kind of switch, the transistor, most times shown like this. But before we get into it, let's look at the wiring diagram of the lamp and the switch. This is how it is wired. We have our voltage source on the left, our switch on the bottom, and our lamp in the middle. The door obscures a small portion of our wiring, but that's a straight line there. For my engineering geniuses who are already advising me to connect my switch conventionally to the positive instead of the negative, thanks for being so observant and outspoken. I appreciate that, but it's connected this way intentionally just so I can illustrate this better. If you have any other thoughts, questions, or corrections, please do not forget to leave it in the comments. Notice how one terminal of the lamp is connected to the positive of the source, but it doesn't light up. There is already current flowing in this branch of the circuit, but it doesn't light up because that current is being opposed by a point of high resistance at the switch. For the lamp to light up, we need to flip the switch, thus eliminating the point of high resistance. This is very similar to how a transistor functions. For a bipolar junction transistor, popularly called BJTs, we could connect a LED to the collector and our emitter to ground. You might expect the LED to light up, but that won't be the case because there is no current flowing in at the base terminal. But if we connect a conducting part at the base, as soon as there is current, the LED lights up instantly. Just like the mechanical switches in your homes require you to physically flip it on and off, the transistor is an electrical switch, and the way to switch it on is to send in a current at the base of the transistor. This is why it is sometimes referred to as a current controlled current device. I used to ask myself why we use a transistor instead of just simply connecting the circuit like this. Same result, easier and cheaper to implement. If you are that guy who still wonders why, here's an answer for you. Transistors require a very small current to be switched on, usually in microampere, and they have a current gain characteristic often referred to as beta or HFE. This current gain allows us to control higher currents using a very small current signal. In my experience, you will mostly find general purpose transistors to have a current gain of about 100. Now that we know this, let's look at a basic example using their schematic symbols. The LED connected to the collector is just to indicate the flow of current and serve no further purpose. On the left is circuit A without a current signal at the base. The LED is off, and on the right is the same circuit B but with a current signal at the base. Notice the LED is on to indicate the flow of current in circuit B. If we take circuit B and we add an emitter resistance, the circuit becomes like this. We can then use the voltage drop across the emitter resistor to switch on another transistor just like this. And why not add two more in the same sequence? Now we have this. Why don't we connect all our ground nodes to a single line and all our VCC nodes to a single line as well? Now let's take out all the repeating symbols for ground and VCC. Next, let's name our transistors Cure1, Cure2, Cure3, and Cure4. Notice that we also do not necessarily need these two voltage sources. We can remove the voltage cell at the base and just connect to VCC. It should work just fine. As we earlier established, the LEDs serve no further purpose than to indicate the flow of current. And since we already have a good idea of how the circuit works, I don't think we need them anymore. Let's connect voltmeters and test the outputs from the different transistors. We have an output of 9 volts at our final output. Let's spice things up. Some of us may have discovered the pattern already, but for those of us who are a little slow, let's catch up. If we put a push button just at the base of every transistor, we could create a combination of code. First, let's begin with Cure 1, Cure 2, Cure 3, and then Cure 4. Now let's begin our simulation and see. Did you notice that when we press the button at Cure 1, the output goes high, but when we release the button, the output quickly falls back to zero? We need a strategy to delay this voltage drop. That's right, I know what you're thinking. Capacitors. Let's connect a capacitor at the base of every transistor. Now let's run a simulation again and see. From these two alone, you can see that the charge and discharge time of the capacitors is too small. They charge and discharge extremely fast. This is due to their small capacitance. Let's send their values up to 400 microfarads. Here we have it. At this point, maybe we should take out all the voltmeters since we are done with the testing phase. Great, we just created a password combination circuit using 4 transistors. But to take things even further, let's build a reset circuit. This will contain all the wrong buttons that are not in the combination. We could just connect push buttons in parallel with the capacitors at the base of each transistor, just so that when a wrong button is pressed, it should act as a short circuit across the capacitor terminals, bringing the voltage down to zero. But how efficient would that be? We need a way to short circuit all the capacitors at once each time a wrong button is pressed, and I have just the perfect idea for it, or almost perfect. We are going to use transistors, PNP transistors. If you have watched my previous video, then you must know that transistor is my middle name. We will just go ahead and connect the collector of each PNP to the base of an NPN. All emitters are sent to ground. Next, we connect the base of all PNP transistors together and we add a reset button linking it to the ground. All buttons not found in the password combination will be connected together in parallel and used as resets. This circuit works perfectly, and if you implement it just the way it is 100% going to work. But just because something works fine doesn't mean it cannot be improved. Let's make our circuit more concise. We can simply just charge up our first capacitor and use the first to charge the second, and the second to charge the third, and the third to charge the fourth. With this setting, we will only need to use a single transistor. To illustrate this, let's begin with our transistor cure. Next, we place our 4 capacitors, each of them with a capacitance of 47 microfarad. Let's connect the emitter of our transistor with the negative terminals of our capacitors. Now let's move to figuring out how to go about with our connection. First, I'm going to increase the spacing between these capacitors because I can anticipate some connection in between. We are going to connect a push button in series with every capacitor. Let's connect the base of the transistor to the closest capacitor. We should also not forget to include a current indicator, which is a LED, and set up the first capacitor for charging. Now we will connect the positive of every capacitor to the preceding push button. That's it, a password combination circuit designed with a single transistor. Now let's focus on the reset circuit. We are going to do the reset circuit exactly like the previous one. I hope there are better ways to do this. If you have an idea, please leave it in the comments below. Now we are going to connect the power source, run a simulation, and see if everything checks out. Everything checks out. We're good. The last step is to take out the LED and introduce an emitter resistance. We've successfully designed a password door lock using transistors. You can add an amplification circuit at the end to be able to drive solenoid lugs, drive motors, or any other device you might want to control. I will advise you to build a 555 monostable circuit so that the output is only a pulse to set your timing. That is it for this video. Thank you for making it to the end. This is Fitech. Please like, subscribe, share your thoughts, share the video. Stay blessed.